This time we're going to look at another neat aspect of synthetic division, another nice neat little theorem that goes right alongside synthetic division. It is the Factors Theorem. So our problem here, it says show that x minus 2 is a factor of that long polynomial. So to show it's a factor, well, we're going to divide it and show that it divides nice and evenly. And that's what the Factor Theorem says. It says some polynomial f of x, it has a factor x minus k if and only if f of k equals 0. Okay, so the only way x minus k is a factor is if when you evaluate at k, the result is 0. Well, how does this relate to synthetic division? Well, we previously saw how the remainder theorem says that if I divide by x minus k, the remainder is the same as evaluating at that k value. So if I go through synthetic division and I get a remainder of 0, that means f of k is equal to 0. And furthermore, and what we really care, that means that x minus k is a factor. That means that number we divided by with our synthetic division is a factor. And while this is kind of obvious, and you'll see it with your beginning work of synthetic division, how if it divides evenly into it, it's a factor, it's good to state it for sure and have this theorem to back it up, because this really is the meat of what we need this synthetic division and polynomial long division for. It helps us break down a polynomial down into its factors. So if I want to show x minus 2 is a factor of that long polynomial, I will have to use synthetic division and hope that it returns a 0. So I will list out my coefficients: 2, 7, negative 4, negative 27, negative 18. Also, just keep in mind, this is of the form x minus k, so it's proper to use synthetic division with this. All right, here we go. Drop down the 2. 2 times 2 is 4, and then add. And 2 times 11 is 22 as we repeat the process. That would be a positive 18. 2 times 18, 36. Negative 27 plus 36. Ooh, this is looking good. 2 times 9, positive 18. Remainder 0. That tells us two things. It tells us that f of 2 is equal to 0. And by the factor theorem, that means x minus 2 is a factor. Sweet. So we have shown that x minus 2 is indeed a factor of that long polynomial. Okay, great. So we answered the problem. We showed that x minus 2 is a factor. Well, that's cool and all, but we can take this a little bit further. So instead of just asking to show that a single factor is indeed a factor of a polynomial, let's answer the question or the statement, factor this function, given that x equals 1 is a 0. So I need to factor this one in its entirety. And we're going to see we can actually do repeated synthetic division on that polynomial to break it down. And this is really important because this is how we're going to find all the zeros of a polynomial, or find all the factors of one. Okay, so given that x equals 1 is a 0, well, that means I do know that x minus 1 is a factor, but then what is everything that's left over as I factor out x minus 1? Okay, so I can figure that out by doing synthetic division. I'll list out my coefficients: 15, 1, negative 52, 20, and 16. And there are no missing powers, so we're good to go. Drop down the 15. 1 times 15 is 15. 1 times 16 is 16. Negative 52 plus 16, negative 36. 1 times negative 36 is negative 36. Get a negative 16. Good. It evaluates to 0. That does in fact confirm that x minus 1 is a factor. that x equals 1 is a 0. But more importantly, it tells us that we have this new polynomial left over. 15x cubed plus 16x squared minus 36x minus 16. And that, how did I know to start at x cubed? Well, that's just one less than the highest power in our original function. Okay, well, that's good and dandy. But now, how do I factor that further? There's 4 terms, so I could factor by grouping. Maybe that'd work, maybe it wouldn't. It doesn't always work. But I can do synthetic division again on that. The only question is, what should I divide by? What is my next factor like this? Now that question can be answered with something called the possible rational roots theorem. And we'll talk about that later. And that's how we can come up with a new guess, because should I divide by the factor x minus 2, x plus 2, x minus 3, maybe x minus 1 again? How do I know? And that possible rational roots theorem, that helps you with that. For now, let's just say I cheated a little bit and I know that negative 2 is a 0. So let's divide this again. See what we get. 15, 16, negative 36, negative 16. And let's go through synthetic division again. Get negative 14 times negative 2, positive 28, negative 8. Okay, good. It worked out again. So I have yet another polynomial, 15x squared minus 14x minus 8. And let's just to be sure, off to the side. So this tells me that x minus 1 is a factor because that divided. This tells me that x plus 2 is a factor because negative 2 has a 0 divided out evenly. Okay, so currently I'm left with this polynomial 15x squared minus 14x minus 8. This is a trinomial. So if this factors, we know how to deal with that because we know how to factor trinomials. Okay, the lead coefficient is not 1, so we'll multiply that back term by 15. We get negative 8 times 15, negative 120. Okay, so now we've got to find factors of negative 120 that add to negative 14. And after a bit of thinking, you might come to the realization that it is in fact negative 20 and positive 6. So we'll split up our x term to that. And then we can factor this by grouping. So I'll factor out the common term, the greatest common factor out of the first two. Looks like 5x. And I'm left with 3x minus 4. And then I can factor a 2 out of the next guy. I'm left with 3x minus 4. Okay, great. These match up, and then I'll take the terms on the outside for the other factor. So 5x plus 2 times 3x minus 4. So I didn't have to use synthetic division on this last step, on this last polynomial up here. That's because there's a trinomial and I knew how to factor that. But let's once again take an appraisal of the factors we have. I have those two factors. I have x plus 2, and I have x minus 1. So starting way up at my big polynomial up here, my 4th degree polynomial, I slowly broke it down with 2 synthetic divisions and then factoring of a trinomial. I broke it down enough in order to see that I have these 4 factors. So in the final form, I can say that in fact f of x equals x minus 1 times x plus 2 times 5x plus 2 times 3x minus 4. And that right there, that whole long string, is the same as our 4th degree polynomial up here, just in its factored form. So pretty neat. I can use repeated synthetic division to completely factor a polynomial. And just for kicks and giggles. We can also say this function has the zeros, x equals 1, negative 2, negative 2/5, and a positive 4/3. Those would be the 4 zeros of that function. I did that by setting each factor equal to 0. A lot of cool things we can pull out of our syntactic division, and it makes it nice and quick and easy to do.